Hi, let's talk about the topic of fluids at rest, which I always thought was a kind of silly name for a topic in a physics textbook because if you think about the definition of a fluid, fluid means freely moving around. So how can something freely moving around be at rest? Well, what we mean by at rest is that there's motion, but there's no order to the motion. So if I were to draw some sort of arbitrary box of fluid, the total number of molecules at any given time inside that box would be constant. So if any fluid moved in, some other fluid would move out. And there would be no organization to it. All of the molecules aren't going from left to right or up or down. That would be an example of what we call currents in fluid. There's also no organized rotational motion, no whirlpools or vortices or eddies. The molecules are all moving in evenly distributed amounts. So the net momentum is zero, the net angular momentum is zero, the center of mass isn't doing anything, and nothing is happening around that center of mass. So, if that's the case, here I have this box of fluid sitting in fluid. Well, for any object to be at rest and to stay at rest, that means that by Newton's second law, the sum of the forces acting on that object have to equal zero. Well, I said that this is a box inside some fluid. So all along the top, there would have to be collisions happening with collisions of the fluid molecules along the top of that box. There would be a pressure there, and there would be a force pushing downward on the top of that box that would be equal to the pressure on top of the box times the area of that box. On the bottom of the box, again, collisions are happening. There would be pressure at the bottom of the box, and there would be a force on the bottom of the box equal to the pressure on the bottom of the box times the area, and that force would be upward. And that box is full of stuff. Any object made of stuff is subject to a force of gravity. So we would also have to be dealing with the weight of the fluid inside that box, the mass of the fluid times the strength of gravity. So from Newton's second law saying the sum of the forces are equal to zero, we'd have forces on the side. I'm conveniently ignoring them because they would be pushing against each other and cancel out. Now in the up and down direction, the upward forces, the pressure on the bottom times the area, equals the downward forces. The pressure on the top times the area plus the mass of my fluid times gravity. Now with fluids, we normally don't think about mass. We normally think in terms of density. And the density is the mass over the volume. So the mass of my fluid would be the density of my fluid times my volume. But for the volume, I said there's some sort of area over which that pressure is acting to give me a force. So the volume of my box, if I have some change in height, y1 minus y2 or y2 minus y1, depending on how you want to think about those numbers, I'll just throw in an absolute value here just to say the magnitude of that change in position. Well, my height times my area gives me my volume. Pressure times area, a whole bunch of other stuff times area, the area cancels out. It doesn't matter how large an object is, the pressure at any given level inside a fluid that's at rest is going to be uniform. And in physics we sometimes say fluids seek out their own level. That means if it's at rest, you can draw a horizontal line and the pressure along that line would have to be exactly the same as long as there is fluid sort of physically connecting all of those points. So the pressure on the bottom is the pressure on the top plus the density of our fluid times the height of that box of fluid, our change in our y-coordinate times gravity. So if we were to just extend this all the way up to the surface of our fluid, we could be at atmospheric pressure, we could be at any pressure. We'll call that arbitrary pressure P0. Pressure where we are at zero depth in our fluid. So if we measure our depth using a D for depth, the pressure at our depth is the pressure at a depth of 0, our surface pressure, plus the density of our fluid times the strength of gravity times our depth. So how is it then that we measure pressure in terms of a height of mercury? Well, to make a simple barometer, all you need to do is dunk a glass or any container inside a fluid, get all of the air out of it, fill it completely with fluid, flip it upside down, and draw it out of the surface. And if you do that, the atmospheric pressure pushing on the surface of this fluid is going to push that fluid up and into that container. Now, it'll keep doing that until one of two things happens. You run out of glass, and if you've ever played around doing dishes, you pull the glass all the way out of the water comes instantly rushing out of the glass. Now, the other thing that could happen is that you run out of pressure. And as you keep going up, you would hit a pressure of 0, and we can't have negative pressure. The lowest absolute pressure corresponds to no collisions, which is what we would call a vacuum. So the height of the fluid that it would take to get down to the pressure of our exposed part is a measure of our atmospheric pressure. So with mercury, at atmospheric pressure, you could lift a glass of mercury out of a giant puddle of mercury, and it would stay, the mercury, at a height of about 760 millimeters, depending on atmospheric pressure. Atmospheric pressure goes down, the mercury sinks, because there isn't as much force pushing it upward. The pressure goes up, the mercury goes up, because it's able to lift that mercury to a slightly higher height. Thanks for watching.